Mean or average value of AC. It is defined as that value of direct current which sends the same charge in a circuit in the same time as is sent by the given alternating current in its half time period. That means for DC, if the charge sends Q in time t, that would be equal to the same charge in AC for its half time period. That means t by 2 is equals t. This is for AC and this is for DC. Charge sends is Q. In that case, for AC, we will say it is the average value of alternating current, or we can be write it as I average or IM, that is the mean value or I average value. Now let's find the relation between average value and peak value of AC. First of all, the value of alternating current at any instant t is given by I is equals I naught sine omega t. So this is the instantaneous value of AC current. Now this current can be assumed to remain constant for a small time dt. So we can assume that this current for a very small time dt, for a very minute scale, it is constant. We can assume that. Then the amount of charge that flows through the circuit in small time dt will be, that can be written as dq, and we know that dq is equals I dt. For dt time, charge flowing is dq, so we can get the small charge dq for time dt. Now let's replace I naught sine omega t and dt. Now the total charge that flows through the circuit, say in the first half cycle, so for AC, this is our complete cycle and this is our 0, this is our t by 2 and this is our t. So the total charge that flows through the circuit, say in the first half cycle, so this is the first half cycle, that is from 0 to t by 2. So our t equals 0 to t by 2, and that is given by q equals integration 0 to t by 2 dq. Let's replace the value of dq, I0 sine omega t dt, and integration 0 up to t by 2. I0 is constant, so integration of sine omega t dt is integration sine x dx is minus cos x. So here it is sine omega t dt, so it will be minus cos omega t divided by omega, and limit is 0 up to t by 2. Now omega is our 2 pi by t. We can take the omega outside, so it will be I0 divided by omega. In this case I0 divided by omega, then omega is our 2 pi by t, so this is our 2 pi by t, and we can replace the omega here also, so it will be 2 pi by capital T into time t, and we have taken the minus sign outside. So it will be I0 t will be in the numerator, so I0 t by 2 pi, and if we replace the now if we put the limit, so it will be our cos 2 pi by capital T into t by 2. First of all, upper limit, so it will be cos 2 pi by capital T. Let's replace the value of t, so it will be our t by 2. T and t gets cancelled, 2 and 2 gets cancelled, so we get cos pi, and in the lower limit, so it will be cos 0. Now cos pi is negative 1, minus cos of 0 is 1, so it will be minus 1 minus 1, so it will give us minus 2, and minus will get cancelled, and 2 and 2 gets cancelled, so it will be I0 t by pi. So we have the total charge q. Now the average value of AC over the first half cycle is So average value I average will be charge over time. So charge is our Q and time is our first half cycle, so it is T by 2. So T by 2. So it will be 2Q by T, and then 2 by T into Q is I0 T by pi. So it will be our T and T gets cancelled. So it is 2 by pi I naught. 2 by pi I naught. And 2 by pi is 0.637. So we get the I average value, that is I average is equals to 2 by pi I naught, that is equal 0.637 I naught. This is the relation between the average value and the peak value. So this means that the average value of an alternating current is 2 by pi or 0.637 times its peak value. So we get the average value as 2 by pi times the mean value. This similar situation can also be proved for alternating EMF, and in that case we will get E average, that is equals to 2 by pi E naught. So it is 0.637 E naught. This is the relation between the average value of AC with the peak value.